Okay, in this video we're starting section 4.1, which is forced harmonic oscillators. Moose, our maskless mouse, is very, very excited about this. Chapter 4 is his favorite chapter in the entire book. Okay, and that's because when we've looked at our harmonic oscillators, unless they were undamped, in which case they just oscillated forever, and Moose was kind of okay with that, okay, if there was a damping force, the origin was always a sink. Okay? So the ride was kind of getting more boring as time progressed. Sometimes it was a spiral sink, sometimes it was just a sink, but both the position and the velocity were approaching zero. Okay? So it ceased to be a really exciting ride for poor Moose here. Okay? Well, let's just remember what our general harmonic oscillator looked like. We had my double prime, that was the total force. And then we said there are two forces that always exist in nature. There's going to be the damping force. That's the combination of friction and air resistance. Here, B is a positive parameter. The damping force acts in the direction opposite the velocity, so we have to introduce that negative sign. And then minus K times Y, this is the restoring force. So every spring comes with a spring constant K, which is positive, but the restoring force acts in the direction opposite the position because it's trying to put you back in the rest position. Okay. So this is what we started with. What we're going to do now is we're going to add another force. So essentially, this is somebody coming along and saying, poor Moose. Moose looks bored because the ride is not particularly exciting. Let's give a push. Okay. So we're going to add some external force to give Moose a more exciting ride on this mass. Okay. So I'm just going to rearrange the equation a little bit. We're used to, if we had zero here, so this was homogeneous, we're used to adding those guys over. I'm still going to add those guys over, but I'm going to keep this new force on the right-hand side. So that's going to give me my double prime plus by prime plus ky equals f of t. And usually we're going to divide by the mass because we know that's not zero, so we can, just because that gives us a more convenient form. That's going to give us a coefficient of 1. Now when we do that, what we'll get is y double prime plus py prime. So here P is just going to be B over M, plus Q times Y, so here Q is just K over M, equals G of T. So G of T is just F of T divided by M. We usually call G of T the forcing function. That's a bit of a misnomer because the force that we're actually adding is F of T, but we call G of T the forcing function. We just scale everything by the reciprocal of the mass just to make that coefficient 1, which makes our life a little bit simpler. Okay, so this is the sort of differential equation that we will be solving. I'm just going to refer to that as star. And just like when we had a first order case, there's going to be an associated homogeneous equation. That would be just y double prime plus py prime plus qy equals 0. That would be if we zero out this external force. That gives us our associated homogeneous equation. Okay. So I want to just go over a little bit of vocabulary for the type of equation that we have and talk about how this relates to the similar situation we had in the first order case and see if we can generalize some stuff from there. So this equation, not the associated homogeneous, the original equation here, is second order. Okay. It is linear because every term is just some y's, some y primes, some y double primes, or a function of t. Okay. So it is still linear. What it is not is homogeneous, because there is a term that is a function of t that is not a coefficient in front of y or one of its derivatives. So that's what's new. It's not homogeneous. In general, this is probably not going to be autonomous either. It could be. G of t could be a constant. If so, then I would still have an autonomous equation. But if g of t is e to the t or cosine of t or t squared, and I have to write t in order to write that, then this would not be autonomous. It is constant coefficient though, because we've got constants in front of our y prime, and our y double prime. Okay, now if we think back to a similar situation we had with first order differential equations. If we had y prime equals ay plus b of t. Okay. So this was a first order first order differential equation. It was linear. Assuming this was not constant, it was not homogeneous, but it was constant coefficient because I've just got one copy of y prime and a copies of y. Okay. And we had learned that we had an extended linearity principle. So again, we had the associated homogeneous equation, which was y prime equals ay. We were able to get by inspection that solutions to that were just k copies of e to the at. Now, our associated homogeneous equation here isn't quite as simple. We're not going to just look at it and say, oh, I see the solutions, but we have developed techniques for finding solutions to the associated homogeneous equation. Okay. And what the extended linearity principle said was that if we could find a particular solution, and we usually did that by just guessing, okay, then the general solution was just y equals y sub h plus y sub p. That was by the extended linearity principle, which basically said if you have a solution to the associated homogeneous and a particular solution to the original differential equation, you add them together, you've got a solution to the original differential equation. And all solutions can be built that way, so that this is the general solution. This isn't just some of the solutions, it's all of them. So it would be very nice if we had an extended linearity principle for second order systems as well, and we do. I want to just emphasize that linearity is always going to apply to homogeneous systems. So I do have a linearity principle for second order differential equations. Our book didn't ever state that directly. They sort of did that indirectly by proving the linearity principle for the associated systems of differential equations, but then that translates back to the original second order differential equation. So linearity just basically says if I have solutions, any linear combination of solutions to the homogeneous equation will also be a solution. That actually makes some sense. If I have something and all of these things add up to 0, if I were to multiply the function by 5, I'd multiply all the derivatives to 5, they'd now add up to 5 times 0, which is still 0. If I had two solutions, all of these things would add up to 0 for one, they'd add up to 0 for the other. When I add them up, they add up to 0 plus 0, which is still 0. Okay. But if I have a non-zero function here, if I had a solution to star, and I multiplied it by 2, I'd be multiplying y and y prime and y double prime all by 2. They wouldn't add up to g of t. They'd add up to 2 times g of t. So linearity applies to homogeneous systems. Extended linearity applies to non-homogeneous systems. So what I'm going to do right now is just state the linearity principle, and then in the next video, or the extended linearity principle, and then in the next video we'll prove it. So it comes in two parts. One, it says if y sub h is a solution to the associated homogeneous equation, and y sub p is a solution to star. I think of that P as standing for that's a particular solution. It's usually a particular one that I managed to guess. Then y sub h plus y sub p is a solution to star. And the second part says if y sub p and y sub q are both solutions to star, then the difference between them, y sub p minus y sub q, is a solution to the associated homogeneous equation. And it takes a little thinking, but that tells us that every solution can be written in this form. Okay, that's an indirect way of saying, hey, if you do this, you're going to get all solutions. Okay, how does that work? Well, if I have y sub p, and I say that's my particular solution, so I want to say that everybody's solutions can be written as my solution plus a solution to the associated homogeneous equation. Somebody says, well, what about this solution? Then I say, well, yq is the same as is the same as yp plus yq minus yp. Okay, that's my solution, and this is going to be a solution to the associated homogeneous equation. Now over here I wrote yp minus yq, but the names were arbitrary. It basically said if you have two solutions and you subtract them, it's a solution to the associated homogeneous. So this would be a solution to the associated homogeneous, and I can write that solution as mine plus an associated homogeneous solution. All right, we'll prove this in the next video.